Hi guys, we are going to talk about vector fields. So we're getting into chapter 17, the last chapter, yay, finally, of um this class, this course. So we are going to be talking about vector calculus. So we're going to look at, this idea of a vector, obviously, that we talked about for a long time in one of the chapters. I don't know, it's all blurring together now. But in one of the chapters, we talked about vectors. We did a lot of stuff with vectors, dot product, cross product, all that stuff. And now we're going to say, well, can we actually do calculus over vectors? So, and what does that even mean to do calculus over vectors, right? So the idea is that we're actually going to look at calculus of something that we call a vector field. You've probably heard of a vector field before. I'm sure all you kids are talking about them. But a vector field basically is something that is, well, let's just define it kind of, not formally, but a vector field, we'll have a formal definition for it. But a vector field really is just a function describing a collection of vectors. And a lot of times, a collection of vectors, and a lot of times those vectors are velocity vectors. Okay, because remember, what do we know about a vector? It has magnitude and direction, and a lot of times that magnitude is going to be velocity. That just makes sense. So for example, you could have a vector field. Well, let me actually show you a picture that they have in your book. So these are 3 examples from that your book gives of vector fields. So they probably look familiar to you if you've ever watched a weather forecast, right? They'll show you like what the jet stream is doing. That's an example of a vector field. So in part A here, this is a vector field that shows the wind pattern of the hurricane. So you can see these little arrows right here, right? These are vectors, right? They have a direction and a magnitude. There are arrows right here also, and then of course these arrows in here too. The longer the vector, that means that has more magnitude or more velocity. Okay, part B is the circulation of water in a heat exchange, and then part C, which I thought was kind of interesting, is the gravitational, magnetic, and electric force fields can be represented by vector fields. Okay, so you've seen vector fields before. We could use vector fields for a lot of things. Anything that has a direction and a magnitude. We could look at the transport of a chemical pollutant in a lake. We could actually use it to show human migration, right, from back in the day or now from different states or from different countries. Okay, so let's talk about this more specifically, but that's what we mean by a vector field. I guess not more specifically. Well, there's some from my office hours. Not more specifically, let's talk about it more mathematically, okay? All right, so here's the definition of a vector field, the formal mathematical definition. You might pause, write it down, and then we'll chat about it. So the definition, welcome back, yeah? So we have 2 functions really that are going to define our big function for the vector field. So let f and g be defined on some region in R2. Okay, so we're in the xy plane. Then a vector field in R2 is a function f. So notice there's a line over that. So that's going to be a bold f because this is basically going to be made of vectors. That assigns to each point in R, so that little subset of R2, or maybe all of R2 it could be, assigns to each point an actual vector. Okay, and so notice our notation here. We're coming back to vectors. We have those pointy brackets, that's totally what they're called, where how do I get the x coordinate for my vector? I take f of x and y. How do I get the y coordinate? I take g of x and y. How do we write this? Well, we can write it, with the pointy brackets, or we can write it with the ij notation. That's fine with the I hat and the j hat. Okay, so we're used to seeing that, I think. So it's a vector valued function. F is continuous or differentiable on R, depending on the continuity differentiability of f and g. Okay, so it's going to be continuous or differentiable if f and g are continuous or differentiable on R, which I hope makes sense. Okay, also just to let you know, if you hear like children screaming in the background, I promise that's just my husband wrestling with them in the basement. So I got out of that because I had to come and do this. Okay, so really quick note about this. Whoa, I don't need green probably. Note. Come on, Microsoft. I'm trying to talk to my husband and getting me the new iPad, but it's not going very well. Okay, not that I don't like my Surface, but I'm more of a Mac girl. All right, F cannot be represented by a single curve or surface. It has to be a bunch of vectors, okay? It's not a single curve or surface. How do we find F? We plot the representative vectors, which means we could have a lot of them, right? So let's look at some examples of plot of some vector fields. So let's say that F of xy is given by 2x, 2y. Okay, so basically what we want to look at is what is happening to this for some x and y value, all right? So here's how we want to do this. So for 0, 0, right, obviously what am I going to have at 0, 0? I'm going to have the vector 0, 0, which isn't super exciting. Let's look at the vector 1 half, 1 half. What would I have? I would have the vector 1, 1. But remember that's 1, 1, and it's going to be starting at the point 1 half, 1 half. Okay, so that's what you have to be a little bit careful of when you're dealing with this vector fields. I want to get a good axis here really quick. I don't know why I care all of a sudden, but there's x. Ooh. Let's bring that down a little bit. That was an x. That was y. I'm gonna put that away, and then I'll just. I could. Well, yeah. Let me do that really quick. Okay. So at 0, 0, we have the vector 0. Now let's look at what happens at 1 half, 1 half. I have the vector 1, 1. So normally, right, my vector 1, 1 would be this guy right here, but I want that vector to actually start at 1 half, 1 half. So that's what we mean by. My scale doesn't look that great. Sorry. That's what we mean by finding that vector field, right? Is at 1 half, 1 half, I'm actually going to go over 1 and then actually up 1, right? So I'm going to have this vector right here. Likewise, what would I have at negative 1 half, 1 half? I would have the vector negative 1, 1, right? So if I normally have the vector, negative 1, 1 is normally right here, but what I'm going to actually do is I'm going to move it and I'm going to have it start at negative 1 half, 1 half, right? So again, I'm going to go over 1 and up 1, and I'll have this vector right here, okay? Likewise, if I did negative 1 half, right, you can kind of see what's going to happen here. You can verify those. If I go even further in, so if I looked at something like 1/4, 1/4, so you can see we could get a lot of these. 1/4, 1/4 is going to go to 1 half, 1 half. That's a vector. So at a fourth and a fourth, right, I'm going to have here, I'm going to go a half and a half. So again, at a fourth and a fourth, a half and a half, I would have something like this. Okay, and technically they would be, you know, on each other there. What about at 1, 0? Well, if I put in 1, 0, right, at this point right here, if I put in 1, 0, then I get 2, 0. So I would be out right here. Same thing at 0, 1. I would be up here. Same thing at negative 1. So notice the length of my vector would be 2, right? I really messed up that scale a little bit there. If I put in 1, 1, right? So you can see, like, I could put in 1, 1, I'd be kind of right on here. I'd be at 2, 2. So I would go up 2 and over 2. So I'd be way up here. Okay, so you can see that I have these vectors, and I could go through and I could look at what is happening to a bunch of those vectors. So let's write down a couple of things that we noticed with this vector field, right? The lengths of vectors, the lengths of them increase as we move away from the origin. That makes sense because we're multiplying the x and y coordinate by 2. Whoa. We move away from origin. So that's true, right? This is what we call, this is actually what we call a radial vector field. And it's used a lot when we talk about the flow of something. Okay, so I hope that kind of makes sense. Let's look at another one. These, I'm not going to really have you graph these that much. So don't like freak out about that or anything. But we need to kind of but we do need to understand the idea of this vector field and what a vector field kind of gives us. So what about, this is an interesting vector field. What if I had the vector field 0x, and I'm not going to spend as much time as I did last time making my system because I actually did like a worse job of it. So I think I'm better at just, I tried to make my tick marks the actual distance away, and then I think I read the ruler wrong. Yeah, no. All right, so let's see what happens to 0x. So at 0, 0, I'm at 0, 0, obviously. What's going to happen at 1, 0? So 1, 0, right, is going to go to 0, 1. So 0 from here, that means 0 in the x direction and up 1 in the y direction. Okay, what about 2, 0? Right, that's going to go to 0, 2. So I'm going to go nowhere in the, again, the x direction. I'm going to go up 2 in the y direction. Same thing for 3. I would go up 3. What if I had a point like 1, 1? At 1, 1, I'm going to get, again, 1, 0, right? I'm going to, nope, 0, 1. So at 1, 1, I'm going to get 0, 1. Look at this. This is really cool. What about at 1, 2? Again, I'm going to get 0, 1, because what does this vector field do? It basically puts your x coordinate in the y coordinate and then makes your x coordinate 0. So at 1, 2, right, which is this point right here, I'm going to have a vector that just goes up 1. So notice if I'm at the x, when x is equal to 1, I'm always going to get a vector that goes up 1. And at 2, when x is 2, I'm always going to get a vector that goes up 2. At 3, obviously, I'm going to always get a vector that goes up 3. And same thing down here, right? I would go up 2, 2, and 3, and so on and so forth. If I look on the y-axis, I'm not going to have anything, right? Because I have anything on the y-axis is going to have the coordinate 0, comma, whatever my number is, right? But then that's always going to give me 0, 0. So I have nothing on the y-axis. If I look in the negative direction, so if I look at like negative 1, 0, what is that going to return? It's going to return the vector 0, negative 1. So now what's just different here is that my vectors are all going to point down. This is, I don't know why, but I like this one. Probably because it's really easy to see. And then of course at 2, I would go down 2, right? I don't know, it's just kind of fun to draw. If you're in a meeting, maybe you could just draw these, because, oh, that was way too much. 2, 3, we would go half, right? Jeez, Sarah. Okay, so this is what we call a shear vector field. And I just think it's cool. I'm sure there's some really important uses for a shear vector field, but I just kind of like I like the look of it. So, oh, look at here. They say in your book, the flow curves for this field are vertical lines. If F represents a velocity field, a particle well, that makes sense. Right of the y-axis moves upward and a particle left of the y-axis moves downward. And then I have a particle, if it's on the y-axis, it's stationary. So, but it makes sense. The further, I don't know if it makes sense, but what this is saying that the further I am away from the y-axis, right, I have a higher velocity and I'm moving up or down, depending on, and if I'm on the y-axis, then I'm not moving at all. I'm stationary. Okay, and then one other one. So I know I'm copying some of the ones from your book, but you don't read the book anyway, so maybe you do. But I'm still going to copy some from your book. 1 minus y squared, 0. And this is for the absolute value of y less than or equal to 1. So the absolute value of y less than or equal to 1, that means y can be between 1 and 1. Okay. So let's kind of see what's happening here. So here's 1 and here's negative 1. So that means that this is 1. That's negative 1, right? That looks about right. And let's see what happens. So when x and y are 0, we're actually at 1, 0, right? So we actually would be at 1, 0. Okay, when, so if I have 0, 0, right, that goes to 1, 0. What if I had, let's just look at a couple of these. What if I had 0x is 1/2 y? So what is this going to go to? 1 minus 1/2 squared is 3/4 0. So at 0, 1/2, which is this point right here, right? I have 3/4, so not quite all the way there. So that's going to be the same down here, right? Because we square it and that's not going to change anything. What if I had 0, I don't know, 3/4? Okay, 0 3/4, 1 minus 9/16 is what, 7/16? So that's almost a half, not quite. Oh man. And that's going to be true for negative 3/4 also. So if I'm right here, I'm almost to 1/2. So I'm probably right about here. Same thing right here, maybe right about here. And what if I had 0 1/4? Right, then I would have 1 minus 1/16, right, which is 15/16. So that's almost 1. So at 1/4, I'm almost at 1. This is a pretty neat one too. I like this. And then actually when you keep doing this, so if we go to x equals -1, what happens is it just kind of does the same thing. It's just going to shift it over here, right? Because we're squaring things. So the my x is going to kind of be the same. We're just going to shift it over, right? Because this is going to occur now with a different, oh, that's really bad. This is going to occur with a different starting point, okay? And this actually is a channel flow. This represents a channel flow. You should also look at, I think that there's the one, this is a really cool one. I'll let you look this up, but why don't you do F equaling, this one's really neat. Why don't you go ahead and sketch the vector field -y, ooh, x. This is a cool one. And I'll tell you right now that this one is a rotation field. So that should give you an idea of what happens with this one. Oh, come on. Rotation field. So you graph that one. That one's actually a really cool one to graph. And it's also in your book on page 1091. So, okay, so we're going to look at a special type of vector field is called a radial vector field. So what the radial vector fields have this property that their vectors point directly toward or away from the origin at all points, except for maybe at the origin, okay? So radial vector fields, again, well, I guess I just said that. We looked at a radial vector field already. A radial vector field that we looked at already was this one up here, where everything points away from the origin, no matter what point you're at. And we have a formal definition for that. I don't totally remember because I haven't taught this in so long, but I don't think we really use this that much. But let's just go ahead and write it down as a definition, just in case we do from now on. This is called a radial vector field. And I'll just pause it really quick while I write down the definition. All right, so here's the definition of a radial vector field. So let's let R be just the regular old vector, right? That basically corresponds to whatever point you're at. So a vector field of the form F, so this is the general form for a radial vector field where you have just some function times R, where F is a scalar valued function, meaning it doesn't spit out vectors, right? It just spits out a number, okay? This is called a radial vector field. So why is this a radial vector field? Well, remember, when we had, so the example that I did for you was 2x, 2y, where what would that have been then? My f of x, y would have just said that for any x and y, it just is going to spit out 2. This is always just going to point out, because if we're at a positive 0.11, it's going to spit out 2, 2, and it's going to stay positive, and that means it's going to go away from the origin. If we're at a negative point, we're going to get 2 negative, we're going to get, because we're just multiplying by a number or a scalar value, we're always pointing away from the origin, and that's what we mean by a radial vector field, okay? Then you notice on this definition, it says of specific interest, or those of the form, basically where what is the scalar function that we're multiplying by? We're going to multiply by the magnitude of r raised to some power. Okay, so if you think about that, what do I know the magnitude of r is? It's the square root of x squared plus y squared, right? And then we're saying we're raising that to some power p. So that's what we mean by the specific type of radial vector field, okay? At all points, if you notice, the vectors point out with the magnitude of 1 over the magnitude of r p minus 1. Well, why would that be true? Because if I'm taking the magnitude of f, right, that's the magnitude of r all over the magnitude of r to the p. So I would take the magnitude of r to the p, the magnitude of the magnitude of r to the p, stop it, is just, it doesn't get changed by another magnitude thing, for real. Now you're just messing with me. It doesn't change by the magnitude because it's just a number. So it wouldn't make sense, right? That would change. And then this is to the 1, so we just subtract them. We're not going to do a whole lot with this, so sorry to kind of waste your time with that. But if you look at like certain types of vector fields like this, like if I had f equals r all over the magnitude of r, right? What that gives us then are all vectors that have unit length. So if I looked at graphing these, right, every vector that comes out would have unit length. Okay, whoa. It wouldn't be affected because what am I really doing, right? Remember, when we divide by its magnitude, we always have a unit vector, okay? And then if we had something like f, whoa, there we go. Let's say is r all over r, let's say cubed, right? What's going to happen as we get out there? Well, as we pick points out, you know, further away from the origin, their magnitudes are going to be greater, right? Because if I have 1, 1 versus 3, 5, the magnitude of this vector here is going to be a lot greater than the magnitude of 1, 1. So actually what happens with this guy is the lengths actually get smaller the farther you get out because we're dividing by a bigger number, right? So that's going to make it smaller. Well, that's not great. Those are examples of radial vector fields, okay? We can also do this all in R3. I am not going to write that down for you. So you should go, well, if you want, or you could just realize that this is true. This all works in R3. Yep. Same, but in R3. This definition is on page 1093. Okay, so basically just defining everything we just did, except now what does our vector field look like? Well, now my input is going to be 3 inputs, right? And I'm going to be spitting out f of xyz, g of xyz. Now, of course, I should have 3 functions, right, that are going to describe the coordinates of my vector. And then you can also have a radial vector field in R3 as well. You just have xyz instead of x and y. And if you look on page 1093, they actually give you some pretty good examples of that also. Okay, last thing in this section, and then that's it. I know we're 23 minutes already, but this is actually nothing new technically. We have already seen what we're talking about. We're just going to now call it a vector field, and we're going to define something a little bit different. And we'll be talking about the potential function again. So gradients, do you remember the gradient? You remember the gradient, right? Do you remember what the gradient was? The gradient of f, let's say if we're in R2, was this, right? It was the partials. So notice what happens when you have the gradient of some function f of x, y, right? It spits out a vector. You guys, we could consider that then a vector field. So let's let phi, okay, so now this is not the phi from spherical coordinates, sorry. Let's let phi be a differentiable scalar function. And a scalar function is just every function that we've known from, college algebra, right? You put in some values, it spits out a number. Okay, so then what we're going to do is we're actually going to define a new vector field, and not new, we're going to actually state that the gradient is a vector field. So for us, we are going to say, let's consider this vector field. What is this vector field going to be? It's just going to be the gradient of phi. Okay, and then what we say is we say that phi is what we call the potential function, and then the f is the gradient field. So let's write this down really quick as a definition, and then I'm going to copy the cool example that I have in your book. All right, so let's let phi be differentiable on a region of R2 or R3. We can define this in either one. Then the vector field f, which is just the gradient of phi, is called the gradient field, and phi is the potential function for f. Okay, so basically what this is going to give us is, if you think about, remember, if I think about a function, I could actually think about its level curves. Remember, the level curves were kind of like, oh, stop. Level curves are just kind of like a snapshot, right, of what's happening. So what this is going to do at every point, if you remember, the gradient gave me a vector that pointed, let's use a different color, and that a vector that was perpendicular to that level curve. Okay, so this would be my phi at some phi of xy, and this guy would be the gradient, the gradient of phi right at that point. So wherever I'm at, it's going to point, it's going to be a right angle with that. And if I look at the vector field that I get here, then what does this vector field do? This vector field takes every single point and points in a direction that actually is perpendicular to the level curve. If you also remember that the gradient pointed in the change, in the direction of the greatest change, right? So that's where a gradient field can be very, very useful, right? If I want to know the direction of greatest change. So let's do a quick example and then we'll call it good. So let's consider the temperature function. If you get into partial, if you take a class on not ODEs, which is ordinary differential equations, but partial differential equations, you talk about this. You guys have probably talked about vector fields. Oh, sorry about that. Maybe in differential equations, usually that comes up. Maybe you didn't. I usually talk about them. Let's consider the temperature function T equals 200 minus x squared minus y squared on some region R, and this region is just going to be a circle centered at the origin with radius 5. Okay, so let's sketch and interpret, whatever that means, right? The gradient field. Okay. So remember, this is a temperature function. So what this temperature does is, let's say we had like a hot plate or something. That's maybe why it's in a circle. And what this gives me is the temperature of that plate, right, at any point x, y on that system. My computer is reacting very slowly to any movement I give it here. Sorry. Okay, good enough. All right, so let's sketch and interpret the gradient field. So let's look at what the gradient field would be. So in this case, it's just going to be the gradient. So the potential function, right, for this gradient field is that temperature function. Okay, so if I look at the gradient of this, I know that the partial with respect to x is a negative 2x, and the partial with respect to y is a negative 2y. Okay, so if I look at what's happening with this, and if you look at the level curves too, right? Remember, level curves can be found by setting this temperature equal to a constant and then solving. So what you end up getting is a bunch of circles. Okay, so 1, 2. Oh, no, stop. 2, 3, 4, 5. 1, 2, 3. I'm glad I can count to 5. You know, with homeschooling, that's pretty good, right? If you look at some of the level curves here, let me graph you some of the level curves. You could actually look at these and see what you got. I think this is when T is 175, right, we're going to have, that circle. Oh, that was really bad. Whoops. Oh, it won't let me get rid of that. We have 180. So anyway, if you look at some level curves here, okay, oh, those are so bad. But if you look at T, what's going to happen is you're going to see that the gradient of T is actually going to start pointing. Of course, it has to be perpendicular, right, to these level curves. But you'll see that these points, if you do that, if you look at the negative 2x, negative 2y, it should be pointing in the opposite direction, right? Because it's a negative. They point toward the center, okay? And so what that's showing is that it's hottest at the center and coolest on the edges, right? Because it's going to point in the direction of greatest change. So it's kind of a cool way to look at that. You should look at example 4 on page 1094 for a much, much better. Oh, well, my puppy is not happy that they're playing without her. All right, so that's example 4 on page 1094. I think that's a good cue to stop because you can hear my dog barking in the back. But the temperatures are hotter toward the center and that heat diffuses outward. It's kind of like cool. We're not going to do the equal potential curves and surfaces on page 1095. You are welcome to look at that. And I hope you have a great day. All right, see you later.